Today we are going to see about working of simple neuron and what is the use of activation function and what are the possible kind of activation functions are available and how it can be used in different algorithms. So first you'll see the single neuron. So usually neurons are represented as a simple circle, even though if it is represented as a simple diagram or in a deep learning network, one single circle represents one neuron. Within the one neuron, the calculation can be done in two parts. So consider then in this circle, we are having n number of inputs. So each input is represented as a x1, x2 up to xn. So in the simple example, two inputs are given. So one is x1, another one is x2. Here in the x1 and x2, some values are given. It may be ranges from 0 to 1, and along with that some weights are associated. So weight also usually given in the range of 0 to 1. If the weight is 0 means the particular neuron does not contribute anything in the cell body. So weightage shows how much the neuron is influencing about the input. Along with that inputs, something is given as a x0. X0 is usually called as a bias. Sometimes the symbol B can be given, sometimes the symbol x0 can be given. And here in this bias, some weightage is given, that is called W0. And within the cell body, there are two calculation happens. One is called as this G. This G equal to summation of weight multiplied with the corresponding input. So in this, as per this diagram, each input xi is having corresponding weight wi, and all the wi is multiplied with the corresponding xi plus this bias. Here what is the bias means? X0 into corresponding weight w0. This is calculated as a bias B. So after calculating, this G will be the input for this neuron. So summated input plus bias is called the input of this neuron, and output of this neuron is F. This F is the activation function. So today we are going to see about this activation function in detail. Usually the activation function, it can be represented as a F of this input. Here what is the input? Summation of weight corresponding input X plus bias. So this is the input for this neuron, and output of this neuron is F. F is the activation function. So the same thing is represented in the mathematical thing. So as I said, Z is nothing but W xi plus bias. So this is the input. Here xi represents all the possible inputs. W is the corresponding weight. B is the bias. Z can be represented as the net input. So the same thing, G and Z are same. In some books it can be given as Z, in some book it was given as Z. So Z and W are same. The output of the neuron is nothing but Y equal to F of Z. This F is the activation function. Now we are going to see what is the use of activation function. So the activation function, it gives the output of the neuron. So usually in the input layer x1, x2, this won't create any output. Apart from that, all the hidden neurons and output neurons always calculates the summation of x and weight, and after this some activation function is applied, that is nothing but our output. So each activation function will give some output. If the activation function gives output, then only the particular neuron is triggered. If the answer is 0 means the particular neuron is not triggered, it is not giving any output. In some cases, one particular neuron always gives output as 0 means that neuron is called dead neuron, because the activation function give a major effect on the neural network's ability to converge to the solution. Converging means how to come to the solution very quickly. So if the neurons activation functions are very good, if they are selected very good, means we are able to come to the solution very quickly. The convergence speed also depends on the selection of the activation function. So based on the application what we are going to develop, we have to choose the corresponding activation function. So as I said already, whenever an activation function is done, the neuron should give above 0. Then only it will be called as fired. If not, the particular neuron is called as a dead neuron. Usually, sometimes not only for giving output, sometimes the output should be normalized within some range. It can be from 1 to 0 or -1 to 1 or 1 to some value. For that normalization also, this activation function can be used. So these are the commonly used activation function. So the first one is simple step function. It gives either value 0 or 1. Linear function usually gives the output like this. So usually we can represent it y equal to mx plus c, like that kind of function. We can use the linear activation function. This can be useful for regression kind of functions. Then sigmoid function, it shows basic non-linearity. Then when comparing to sigmoid, tan shows little bit more non-linearity. And if you are going for deep neural networks, that means we are having input output combinations, and also we want to find the complex relationship between input and output. In such cases, more number of hidden layers are used. In the hidden layers, ReLU is the most desirable one. And there are some little problems in the ReLU. In such case, we can go for leaky ReLU. In leaky ReLU, we are going to use small parameter alpha. The selection of these parameters will avoid dying neuron. Parameter ReLU is also one kind of ReLU. So all these two kinds of ReLU will solve the problems in the rectified neural network. In the rectified linear unit, mostly used for the deep neural networks. So these kind of things, binary to TANH, can be used for simple applications. When you are going for deep neural networks, ReLU and its variants of LeNU can be used. Finally, softmax function. So in the softmax functions, when we are going for classification of multi-classification problem, in this case, we are not having simple neuron in the output. We are having multiple neurons in the output layer. Suppose I want to divide an object into any kind of classes among these three. The output neuron 1 will say some probability, for example 0.1. The neuron will say some output 0.5. The final neuron will say 0.4. So the total probability must be 1. So in this case, I have to choose any one answer from 1. For example, this output neuron may say that the object belongs to car. This second neuron may say that the object belongs to bicycle. The third neuron, third output neuron may say that object may belongs to any three-wheeler. For example, auto. So I have to consider when comparing this value, 0.5 is a higher value, so that I have to classify my input as a bicycle. So for this kind of multi-class classification problem, I can go for softmax algorithm. So this is the basic diagram of all the activation functions. Here all the X represents input and all the Y represents output. Sometimes it is Y is not represented, means this is a standard possible range of output. First one is simple linear diagram. Here X is the input and Y is the output. So whatever values we are giving, that will be directly converted into output. Sometimes the output may be in the format of Y equal to mx plus c. Here in this diagram, simple equation is given by assuming m value is also 1 and c value also 1. The next one is sigmoid. The sigmoid value, whatever we are giving, the output ranges from 0 to 1. This shows simple non-linear. The next one is tan h. In the tan h, whatever the value input x we are giving, the answer ranges from -1 to +1. Next one is ReLU. In the ReLU, whatever the input we are giving, the maximum value of 0 to x will be considered. Suppose we are giving the negative value, the answer will be 0. Suppose we are giving x as a positive value, the answer will be same. Like that it will be calculated. The last one is softmax. In the softmax, we are having multiple values. For example, as we see earlier, we are having more number of neurons in the output layer, especially in the multi-class classification problem. It will give different answer for each output neuron. Wherever we are getting the maximum value, we have to classify the particular input to the particular corresponding neuron answer, which is giving highest value. Now we'll see the activation functions by comparing what is the output range and which kind of applications commonly it can be useful. First, we'll see the linear application. Computationally, it is very simple. So mostly it can be used for regression kind of output. For example, by giving the input like number of square feet and number of bedrooms, we have to calculate the prediction about the price or prediction about the rent. We can go for linear. And computationally, it is very simple. The answer ranges from -infinity to +infinity. Here, the equation f of x just depends on the input x. So calculation wise, it is very simple, but it won't show any non-linearity. It will identify only the linear relationship between the input and output. Next one is sigmoid. Sigmoid f of x can be calculated by 1 divided by 1 plus e to the power minus x. So as we are calculating e to the power minus x, computationally expensive, but it shows little bit non-linearity. The output ranges from 0 to 1. Here we are having the output in this kind of curve. Here it can be 0, it can be 1. Here at the midpoint it crossovers. So whenever we are giving the value between 0 to 0.5, we will get the 0. Above 0.5 means we will get the value 1. So mostly it is suitable for binary classification. And tan H, when compared to sigmoid, tan H is more advanced. The output range is also from -1 to 1. It can be useful for hidden layers in any kind of multi-layered neural networks. But when comparing to all the kind of networks, sigmoid and tan H are computationally expensive and also suffers from one problem called vanishing gradient. Vanishing gradient means when we are training the neuron again and again, whatever the weights calculated earlier may be not influencing in the future calculation. This is called vanishing gradient. This problem will arise in the sigmoid activation function and tan H activation function, and also computationally expensive as we are going to calculate e to the power minus x. In the tan H also we have to calculate e to the power minus x and e to the power positive x. So we have to repeatedly calculate. So because of that, sigmoid and tan H are computationally expensive, but it shows the little bit non-linear when comparing to simple linear algorithm. So next one is ReLU activation function. In the ReLU activation function, when comparing to sigmoid and tan H, it is more easy to calculate because it's just a maximum of 0 and x. The answer can be calculated as maximum between 0 and x. Suppose the negative values are given as an input, it will give 0. If the positive values are given as an input, means the same answer will be the answer of this activation function. So mostly it can be useful for the deep neural networks. So when the deep neural networks are available, except the final layer, final classification layer, we can use for ReLU. And here, what is the problem means, even though ReLU is computationally less expensive, sometimes the dying neuron may be expecting. Dying neuron means sometimes the particular neuron may be always inactive. Always it will give the answer as 0. So this is called dead neuron. So to avoid this case, we can go for some of the variations of ReLU, that is leaky ReLU, e-ReLU, so many variants are available. We can go for that. Even parameterized ReLU is also available. We can go for any kind of this based on the application what we are going to use. The final one is softmax. The softmax, we are having value that provides probability value. Suppose we are having 10 neurons in the output layer, 10 probability values it should give. Finally, the summation of all the values should be maximum 1 as we are using probability. Computationally, it is also a little bit complex. But what is the problem means, if you are having more number of classes, for example, we want to classify the input into one among the 1,000 objects. So we should have 1,000 neurons in the output layer, so that it is very difficult to calculate for all the neurons. So this is the problem in the softmax activation function. But it is very useful if you are going for multi-class classification. So even though it is computationally expensive or non-expensive, based on the application only, we have to choose the activation function. Thank you.